Now we want to talk about unit conversions. These numbers with units that we're going to be working with are real measurements from experiments and from life. And so we're then going to want to take them and do some processing. So we want to talk about how we do math with units. They're a part of the number and need to be considered. So addition and subtraction have a pretty hard and fast rule. You can only add and subtract values with the same unit. So 10 inches minus 3 inches gives you 7 inches. 10 feet minus 3 inches doesn't give you 7 of anything. In order to do that, the units need to be exactly the same, and then you can just do the arithmetic as you would see fit, and the units don't change. So in order to do this, if you have a 10-foot rope and you cut off 3 inches, if you want to figure out how long it is, you're going to need to take one of those and turn it into the other value, other unit. Where we have a lot more flexibility is in multiplication and division, where units multiply and divide in the exact same way as numbers. So for example, if you have, say, 10 meters by 5 meters, the numbers, the 10 and the 5, will combine, and then the units will also combine. So we can see this is m by m, and this is the 10 times 5. Okay, so that would mean you multiply each of those together and they still stay separate. So the 10 times 5 becomes the 50, and the m times m becomes meters squared, right? We use the fact that a value multiplied by itself is squared. So you can kind of see that these units work a little similar to like variables, like in a algebraic expression. Similarly, 180 miles divided by 3 hours. The 180 divided by 3 is 60. Miles divided by hour gets its own special name that we use, mph, miles per hour. So when we combine units in this way, we get what are called compound units. Compound, just like with classifying matter, is when we bring two things together and make a new thing, right? So we've taken two units that independently mean something, and we've made a new unit where they're either multiplied or divided by each other. When we make these compound units, they measure a different quantity than the component unit did. So for example, a centimeter is a unit of length. There's a distance of 1 centimeter. If you take a centimeter and multiply by itself, you get 1 centimeter squared. That's now measuring a 2-dimensional area. If you multiply by itself 3 times, you get 1 centimeter cubed, and that's a centimeter, which is also called a cubic centimeter. So this is a volume unit. 1 cubic centimeter is the size of this cube right here, is literally the size. Each side of the cube is 1 centimeter, so that side is a cubic centimeter. These are often abbreviated as cc. It's really commonly used in it's a volume unit, so pistons and engines is a common place where it's used. The number of cc is the size of the piston, and so but that's just a different unit. It measures something different than centimeter. In much the same way that, miles measure something, hours measures something, miles per hour measures a third thing entirely. It's not a distance or a time, it's a speed. So these ideas of compound units are going to allow us to develop what are called conversion factors. Conversion factor is the ratio of two different units that are describing the same value. So we built some up previously for our metric units. 1 kilogram is equal to 1,000 grams. That was our definition of a kilogram. What that allows us to do is generate this sort of ratio. 1 kilogram is equal to 1,000 grams. So dividing 1 kilogram by 1,000 grams, you're dividing the same value by itself. Those are different unit representations of the exact same mass, so you get 1. What that means, you can multiply any value by 1 and the value doesn't change. So if you can come up with one of these conversion factors, they allow you to change the unit you are using to represent a value. For each equivalence, so here's our equivalence up here, you can make 1, 2 conversion factors. You can see basically the question is, are grams on top or are kilograms on top? So these allow you to convert between kilograms and grams in this case. So with these ideas in mind, we can use a technique for unit conversions called dimensional analysis. And in the world of dimensional analysis, we're going to be multiplying and dividing our units in such a way that we're going to cancel them out to accomplish the unit conversions that we want. We're going to use those conversion factors we built previously. So if we want to convert 5 kilograms to grams, we can see that our starting unit is kilograms and our target unit is grams. And so we can see that this kilograms, if we multiply it by the conversion factor where kilograms is on the bottom of the fraction, this kilograms divides by this kilograms and cancels out. What's left over is the grams that we want for our target answer to be 5,000. We end up with 5,000 grams. So functionally, when we can set up our unit conversions to look like this. And so functionally, when you're doing the analysis, you do 5, the numbers 5, multiplied by 1,000 divided by 1. So you just multiply across the top, and then you divide by whatever's on the bottom numerically. So that gives you the 5,000. And the idea is you rely on unit cancellation to basically figure out where you put all these numbers. And then wherever you put them drives how you actually do the arithmetic. So similar to working with like a fraction, 2 times 5 halves is equal to 5. Multiply 2 times 5, that's 10, divided by 2 gives you 5 again. So the 2's just cancel out. So we're going to look at some unit conversion problems. And when we're working through this, we're going to use a strategy that is going to that I'm going to use for the rest of the term when we're trying to solve problems. It starts with the question of what units should your answer have. When you're trying to answer a problem, you start by figuring out what you want. Then where do you start? What units do you start with? And then finally, in this case, it's what conversion factors connect that start and end point. There may be more than one that we have to use, but this sort of strategy is what we're always going to be working through. So I'm going to put annotations on the slides. We're going to talk about problems, and then I'm going to work them out and show kind of the idea of what I'm doing with the examples. You do not have to go through all of these steps. If you like this method, that's great. Unit conversions you may be comfortable with this and seem that this is a bit overkill, but the idea is we'll build up the strategy now when we're working on problems where we're at least maybe familiar with some things, but when we start to talk about new problems that we're dealing with new chemical concepts, new definitions of units, where we have a kind of a strategy that we can always rely on, at least as a way to get started on problems. So let's look at an example. How many milliliters are in 2.6 liters? Again, we always want to start by asking, what units should your answer have? When we're reading a problem like this, we want to think about what is the answer that we're looking for. We can see there are 2 units given in the problem, ml and L. The fact that ml doesn't have a number associated with it is the indication that milliliters are the target unit. What units do you start with then is going to be the units with a number attached to it, the 2.6 liters. That is a value you already have. You want to turn it in to ml, which is the unit you don't have a value for. What conversion factor connects those 2 end and start points? Well, these are metric units, milliliters and liters, and we learned how to relate those based off the prefix. How many milliliters are in 2.6 liters? So we've already parsed out that what we want is going to be milliliters. How many milliliters? And what we're starting with is going to be this 2.6 liters. So let's see how we actually use that to help us solve the problem. So we know what we can say is we want to do a conversion, and a unit conversion is going to have this general shape, where we take our starting value, we multiply it by some conversion factor, and then we get our target unit for our answer. So we want to have 2.6 liters. We want to multiply it by some conversion factor, and then we get milliliters. And we're going to eventually move to more than one of these, but we know this is going to be a fraction. Right? This is going to be a fraction that relates our two units. So we call that the conversion factor. And so we can figure out what units those need to be. We want to get rid of liters. That means this bottom unit needs to be liters, because you're going to multiply by the top and divide by the bottom, so the liters would cancel out. The unit on top needs to then be our target unit. So it needs to be milliliters, because when we multiply this out, the liters and milliliters will multiply, you'll divide by the liters, so those two would cancel. So the whole idea of this dimensional analysis is by setting up the problem like this, we can figure out that the liters would cancel and we'd have milliliters left over as our unit, which is the goal from the problem. So then the new question is, what numbers go here? And how we get that is, how do we set up an equivalence of some number of milliliters is equal to some number of liters? And that's why we spent time defining metric conversions, metric equivalences, because we can see that these are metric units, liter and milliliter. So we can use our definition of the metric prefixes. You know that milli is 1/1000. So I know I can interpret that. I can say that 1 milliliter is equal to 0.001 liters. So what I do is I take these numbers. The 1 that's next to the milliliter goes right there. The 0.001 liter stays next to the liter. Whatever this equivalence is, those numbers stay next to the respective units. And then I didn't give myself enough room, but that is 2,600. And how I get that number is I take the 2.6, I multiply by the 1, so that gives me 2.6, and then I divide that by the 0.001 liters, giving me 2,600 milliliters. And so what I've done here is, remember, these are equal to each other. So functionally, multiplying by that conversion factor is multiplying by 1. This is a volume amount. This is the exact same volume, just with a different unit. And one of the things about our metric units is we want to start to develop some kind of intuition as to how big they are. A liter is bigger than a milliliter. So this is a small number because these units are big. 1 liter is a lot of volume, so you don't need very many of them to get up to that size. A milliliter is a small volume, so you need a lot of them to count up to that total volume size. I do also want to note that, like we talked about, you could define a different relationship. You could say 1,000 milliliters is equal to 1 liter, and you would get 2.6 liters times, you do the same thing, you want to cancel out your liters, go into milliliters, so that'd be 1,000, and that would be 1, and you would get the same 2,600 milliliters. And you would follow the same, your liters cancel, and you end up with 2,600. And so these are the equivalent relationships. Basically, you just multiply both sides of this equation by 1,000. And you end up with the same conversion factor. So either of those ways would work. I do also, again, want to make a note. You do not need to work through this entire process when you're solving problems. You do need to show work. So you need to show some sort of work along the lines of how you accomplish this. The idea of going through the process of asking what do we want and what do we have is to build a framework to solve problems that we can use as we move forward and getting into things that we're maybe less familiar with outside of these sort of unit conversions. Also just in life outside of chemistry. We're just going to learn some problem solving skills that can help you, hopefully, through the remainder of your life. But the idea is apply to, not crazy, there's not really anything chemical going on yet. So we'll practice applying this algorithm. So that way when we move on to situations where we're doing unit conversions on new types of units, with new types of relationships, we have kind of some tools to help us get started and work through those problems. Participation 6.2, question 3. How many centimeters are in 2.5 meters? This is the third question on participation 6.2 due Tuesday, June 2nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many centimeters are in 2.5 meters? Okay, another participation question. Another one for participation 6.2. It's due on Tuesday the 2nd. We're over halfway through. I think, we're over halfway through. Last video was halfway. Over halfway through the set of videos on the home stretch. Looking for any more participation questions. See you in the next video. Bye-bye.